Okay, let's start. Hello? Okay, let's start. So, in the last lecture, we learned the concept of statistical inference. So, we know that to make statistical inference, we need to rely on our knowledge about the probability, or we need to rely on something called joint probability. And here I have one question. Imagine that we have 3 Boolean random variables. So to specify the joint probability, how many, we can just specify it by using a table. How many entries do we need to specify this joint probabilities? 8. Okay, so 8 is a great answer. But in fact, it's 7, because they all sum to 1, right? So the last entry could be inferred by the remaining 7 entries. Okay, so we can see that to imagine we have many random variables. We can imagine that the number of entries in our joint probability table could be very large. So we will have a large number of entries. And also, if we just naively represent our joint probability by using a table, we sometimes ignore some internal structure of the random variables. So imagine that we have 3 random variables. The first one is the weather, and the second one is cavity, and the third one is toothache. We know the last 2 have a strong interaction with each other. Okay, so we know if you have cavity, it's very likely you will have toothache. But this is sometimes a little bit independent of the weather, right? So this kind of internal structure cannot be clearly represented by just using a table. So we will introduce a Bayesian network, a solution to this scenario. So the Bayesian network falls, generally speaking, Bayesian network falls into the category of method called probabilistic graphic model, or PGM. Okay, so Bayesian network is one kind of PGM. It's not the only one. And the general idea of PGM is to use a graphic model to represent a probabilistic model. Okay, and Bayesian network has many real-world applications. For example, if you want to assess if a customer is a risky driver, okay, so you can just observe a lot of evidence. Okay, you can just represent this evidence as a set of random variables. And then you can use Bayesian network to represent the joint probability, and then you can do the inference. Okay, so Bayesian network is based on 2 important ideas. The first idea is called Bayes rules, and the second one is called independence, or conditional independence. So let's first look at the Bayes rule. Okay, so sometimes it's very convenient to build the statistical model by using causal relationship. For example, if you have a certain disease, then you could know from your domain knowledge, or just from expert, the likelihood of you have some certain symptoms, right? So this could, let's say if you have cavity, you know the likelihood you have a toothache. Okay, so this could be easily obtained by using your experience. So, which means you can easily calculate the following conditional probability, that is P effect conditional on cause. But in many real-world cases, you are more interested in the inverse of the inverse conditional probability. That is the probability of the cause conditional on the effect. Okay, so our question is how to link these 2 probabilities. If you know this probability, how can you calculate this one? Any idea? No? Okay, this is actually quite easy. So you can just use the basic definition of, maybe I can just write down here. So you know P y condition on x. And now you want to calculate Px condition on y, right? So what we can do is we can just use the definition of conditional probability, which states as follows, right? And then you can just rewrite the denominator as Py, right? So this is Bayesian rule, very easy. Okay, and how about the denominator, Py? So you can calculate Py by just use the summation rules, right? And if it's needed, you can just further decompose this as this one, right? So this is Bayesian rule. It's very easy, and the denominator is also can be seen as a constant scaling factor, and you could calculate by just using normalization tricks. Okay, so this is Bayes' rule, and we usually have some names for the various terms in Bayes' equation. So the first one is posterior probability, which means given the observation or given the observation of effect, we want to reasoning its cause. So this is called the posterior probability. And this is likelihood. That is given the cause, that is the likelihood of effect given the cause. And this is called prior distribution. Why it's called prior is because you compare these two terms. Both of them concern the variable x, right? But this is x without any condition. So that is without any observation, what is the likelihood of x, right? So this is called prior probability or prior distribution. Okay, so we can see we have two probability here, two conditional probability here. Both of them have two inputs. Okay, so it's the effect and the cause effect. So will there be any big difference between these two probabilities? Any guess? So it's like, if this is like, let's say 0.1, will this be larger or smaller or have a big difference to 0.1? Any guess? You probably know. Okay, let's have a look at an example here. So this is a quite typical example. That is, you have a disease and you have symptoms, right? And you know the prior probability. That is, someone has this disease. The probability is quite small, right? And you know the probability of just having the symptoms. And you can use the Bayesian rule to calculate the probability here. So now let's compare the two conditional probability here. So this one is the likelihood term, right? So this is your disease, and this is your symptom. And you know this likelihood is actually quite large, 0.5. But when you use Bayes' rule to calculate the posterior probability, we find this one is just very, very small, just a tiny compared to the likelihood. So in this example, we can see that there could be a large discrepancies between the two probabilities. Okay, so this is the first concept I want to introduce. And the second concept I want to introduce is called independence. So there are actually two kinds of independence. The first one is called absolute independence, And the second one is called conditional independence. Let's have a look at the first one. So if we have two random variables, A and B, so if it satisfies the following three, either of the following three conditions, we can see that the random variable A and random variable B are independent. Okay, so let's have a look at them. The first one, it means A condition, PA condition on B equals to PA, which means you can just ignore the condition, okay, and you get the same probability. And this is just same, but just reverse the order. And this one means the joint probability could be the product of the two marginal distribution, okay. So this means the two random variables are independent. And with independence, we can just simplify the joint distribution. Now let's have a look at an example here. So consider three random variables: toothache, catch, and cavity, and also the four random variables, the weather, right? So now let's imagine the last random variable, weather, is independent with the former three variables. And then we can just decompose the joint probability by using the rule of independence. Okay, so this could reduce the number of variables we have, the number of entries we need to capture the joint distribution. Okay, let's say in order to represent this joint distribution, how many entries do we need? An idea? This joint distribution, we got four random variables. Each of them is a Boolean random variables. How many entries do we need? 8. It's actually 8 minus 1, but let's say 8. And how many variables? How many entries do we need to calculate this distribution? If we know this joint distribution can be decomposed in this way. So this could be smaller because then we have 3 random variables here, right? So the number of entries for this one could be just 7, right? Sorry, it could be 5. Could be 5, right? It's 2 times 2 minus 1, right? Oh, 7. Oh, sorry. This one is not 7, right? This one is 15. Okay, but this one we just need 1, right? So the total number of entries for this term is just 8, but this one is 15. So we can see that with independence, we can just simplify our joint distribution. But unfortunately, absolute difference, the independence shown in this one is very rare. So if you have, in practice, if you have a probability model with like hundreds of random variables, usually they are somehow interrelated, so are not absolutely independent. So there is another independence called conditional independence. So conditional independence is similar to absolute difference, but absolute independence, but with one conditional term, z here. Okay. So now we have 3 random variables. This is the conditional probability of the combination of x and y. Okay, so this is the conditional probability of just x and y. So if it is satisfying the following, either of the following 3 terms, we can see that x, y are conditional independent given the third random variable z. Okay, for example, for this one, we can know that the condition y and z is actually not necessary, okay? So if you know z, we can just ignore the value of y. Okay, so this is just same. So this is a conditional independence. So now we have a question here. So if we know two random variables are absolutely independent, will they be conditional independent given another random variable? Any guess? Yes or no? Yes. Okay. The second one, if two random variables are conditionally independent, will they be absolutely independent? No? No. Actually, the answer is no for both. We will see an example maybe at the end of this lecture for the first case. Now, for the second case, we have an intuitive example here. So now, let's consider three random variables. So the first one is catch, and the second one is toothache. So they are not independent. Why they are not independent? Because if the probe catches the tooth, it has cavity that probably cause toothache, which means if we observe catch being true, which may imply someone has toothache, and if someone has toothache, then he is more likely to have. Someone has cavity, then it implies someone is more likely to have toothache. So catch and toothache are linked by the random variable cavity. But if given the presence or absence of cavity, then these two random variables becomes conditionally independent. Because in this case, the toothache will only depend on the state of nerve in the tooth. And the probe, the accuracy depends on the dentist's scale. Okay, so then it becomes irrelevant with toothache. And just like the absolute difference, with conditional independence, we can simplify the joint probability. Okay, now let's imagine we have a joint probability with three random variables. We can just written it in this way. So this is just conditioning rules in probability. Okay, and we can further decompose this into this term. This is just a chain rules. And because the toothache and the cavity are conditionally independent, the catch and the cavity are conditionally independent. So we can just, we know this is just only depend on cavity. Once we know the cavity, this becomes irrelevant. Okay, so we can just decompose the joint probability in this way. Okay, and if we check the number of variables, number of entries we need to specify the joint probability, we will find the number becomes smaller. It's reduced from 7 to 5. Okay, so this is called a naive Bayes model. So this is a very commonly used model in statistical inference, which means given a common cause, all the effect becomes conditionally independent. So one typical application of naive Bayes is for text classification. So imagine that if you want to classify the junk email from the normal email, so you can just imagine types of email, junk or ordinary or normal, as a binary random variable. Okay, so this could be the cause. And based on this cause, you will observe the distribution, the occurrence of some keywords, right? So if one keyword occurs in the email, then it would be 1, otherwise it would be 0. Okay, so this again is a binary or Boolean random variable. Okay, then you can just build a statistical model here. And then you can use the observation, that is the number, the occurrence, frequency, or occurrence of the keywords to infer the types of emails by using the naive Bayes model. Okay, so with the two important concepts, independence and the Bayes rule, we can define Bayesian network. Okay, so the Bayesian network it comprises of the following two factors. The first one is a set of nodes. So because it's a graph, the graph has node. Okay, just like this one. This is the node in Bayesian network. And then we have a graph. That means the node will be linked by edges. Okay, and in Bayesian network, the edges are directed, which means if you have node A and node B, they will be linked from A point to B. But if there is a link from B to A, there will be two different edges. Okay. So the direction is important for Bayesian network. And what does this link means? This means this is usually the cause. The random variable is the cause, and the random variable that the cause pointed to is usually the effect of the cause. So this actually encodes the causal knowledge. Okay, so like in this case, we know cavity causes toothache, and cavity causes catch. Okay, so no problem with this? So this is like the Bayesian network. And the Bayesian network actually reflects a simple conditional independence statement. That is, each variable is independent of its non-descendants in a graph given the state of its parents. So I probably need to explain what is the descendants. So imagine you have a Bayesian network like this. Okay, so this is node A, node B, node C, right? So it's directed. So for node C, you can find a path from A to C by just following the directed edge, right? So C would be a descendant of A. But let's say we have E here, or we have, we have E here. So E would be not, E is not the descendant of A, right? Because you cannot go from A to E by using the directed link. Okay, so you can only go from one direction. Okay, you cannot just reverse the order of the directed link. Okay, now let's have another example. A, B, C here. Okay, so is C a descendants of B or not? Any idea? So C is not a descendant of B because you cannot go from B to C by following the directed link. Okay, so in Bayesian network, let's say we have something like this. X, Y, Z. Okay, so the conditional probability of Z conditional Y, X will equal to PZY, which means that given the parent of the random variable we care about, in this case it's Z, that is, so its parents, its only parent is Z, right? So given Z, we do not, its conditional probability will be not affected by the remaining world, okay? So we have this equation here. So given so this conditional probability will be only dependent on the parents of the random variable x, parents of the random variable xi. Okay. And so in this case, we can just associate each node in a Bayesian network with a conditional probability. Or sometimes in a discrete case, it's just a table. It's a conditional probabilistic table. This is an example. Okay, we have 5 random variable here, right? So each one is associated with that table, and this table is a conditional probability table. For example, like alarm, right? So it has 2 parents, right? So we have this conditional probability, and we have a table here. For B and E, we do not have any parents, so it's just one entry. And this one, right? Okay, so is there any problem at this point? Okay, with the Bayesian network, we can just as I mentioned, we can just include some course knowledge. Now let's have a look at the example here. So this is a scenario. I'm at work. Neighbor John called to say my alarm is ringing, but the neighbor Mary didn't call. Sometimes it's set off by minor earthquake. Okay, so this is a scenario. And in this case, we consider 5 random variables: burglar, earthquake, alarm, John calls, and Mary calls. And by using this Bayesian network, we encode some causal knowledge. It's because a burglar can set the alarm off, right? So this is when the alarm being true is probably caused by a burglar, right? And the alarm can also be caused by earthquake. And once the alarm is off, it can cause Mary call or can cause John call, right? So this is the cause relationships encoded by using this Bayesian network. Okay, and we can just define more fancy and a larger Bayesian network. This is another example. This is related to car start problem, and this is the car insurance risk assessment problem. So we can see there are a large number of random variables here. So you can imagine that if we use the joint probability table to represent this, it could be very painful, right? So there would be so many of entries. And with the Bayesian network, we can just compactly represent the joint probability, or sometimes we call it global semantics. So imagine we have a joint probability for random variable x1 to xn. We can use the basic rules in Bayesian network to decompose it, to factorize it into this term. So we just consider each random variable and its parents. Okay, so we just use this conditional probability and just use their product to represent the joint probability. And to find the parents of a node, we can just use the structure of Bayesian network. For example, what is the parents of Mary calls? It's just alarm. You can just easily read this from the structure of your Bayesian network. Okay, now let's have a look at an example here. So we have a burglar alarm network like this. So what is the joint probability? How could we write the joint probability based on this Bayesian network? Anybody have a try? Any idea? Okay, so let's write it together. First, we start with B, because B has no parent, right? So we know, so to write, okay, maybe I just write this first. Okay, so this is the global semantics, right? So we use this to write the joint distribution. Okay, so we have a network here. Now let's start with B. What is the parents of B? No parents, so we just run PB, right? And then let's go to E. What is the parents of E? No, so we write PE. And then we go to A. What is parents of A? B and E, so it's B, E. And then J is still product. J. It's parents A and A. So this is the joint probability of P, B, E, A, J, M. Okay. No problem with this? Okay, so this is how to write the joint probability by observing the Bayesian network. And with this decomposition, you can just plug in the actual value a random variable can take, and use the conditional probability table to calculate this joint probability. Okay, so this is just plugging in the actual value of these random variables. Okay, so from this example, we can see that by using Bayesian network, because it inherits the conditional independency, we just associate each node with a conditional probability table, and then we can just represent the joint probability. And we will quickly know the number of entries we need to specify the joint probability can be greatly reduced. So in this case, it's from 31 to 10, right? So why it's 10? We know this one has no parents, right? So we just need 2 entries to specify its probability. And because they are summed to 1, so we just keep 1. So this is 1, 1, we have 2, right? So it's 2 power 2 minus 1, 3. And this is 2, this is 1, this is another 1. Sorry, it should be 2. Because they have 2 different conditions. It's A being true or A being false, right? Okay, so this is the number of entries number of records we need to represent a probability, joint probability. And more generally, by using the Bayesian network, we can just reduce, we can just make the number of entries we need goes linearly with the number of nodes. So if we use the full joint probability table, this could be exponential. The relationship will be exponential, right? Okay, so another useful concept is called the local semantics. So that is, we can, by observing the Bayesian network, to rid off some conditional independency relationships. So here is one. So this is the one actually I just mentioned. So each node is conditionally independent of its non-descendant given its parents. It's a little bit tricky to understand. So let's do it by using an example here. Okay, so let's see variable j and m, they are not independent, right? Because they have a common parents here. Okay, but once A is given, will J and M be conditionally independent or not? Any idea? So you can just get the answer by using this rule. So what we need to do is, let's start from J. Okay, so J, let's check J if it's conditionally independent of its non-descendant. So first thing we want to ensure is if M is a descendant of J. Yes or no? Any idea? No. Why? Yeah, that's right. So you cannot go from J to M, right? So this is this is a non-descendant of J. Okay, so the first requirement is satisfied. So we know J is not a descendant of M, and the second requirement is its parents is given. So if A is given, A is the parents of J, then we know the J and M are conditionally independent given their common parents A. Okay, so we can immediately know they are conditionally independent. Okay, this is another property that is called the Markov blanket. So which means a node is conditionally independent of all others given its parents, children, and the children's parents. Okay, so you may wonder why we need to consider the children's parents. And we explain this in the following slides. Okay, so let's consider the following three cases to understand this property. Okay, so the first, let's start with the first one, A and B. If C is given, whether A and B are conditionally independent or not, they were conditionally independent, as shown by in this example, right? But we can use this rule to check if they're conditionally independent. Okay, so let's start with A. So A, let's check A's parents, A's children, and the children's parents. Okay, so A's children, A has no child, right? And A has one parent, C, and C is given. Okay, and because it has no child, so there is no child's parents. So in this case, we know A is conditionally independent of the remaining world. So we know A and B are conditionally independent given C. Okay, how about this one? If C is given, will A and B be conditionally independent given C? Any idea? No? Why? It's not child's child. It's children's parents. Children's parents. So it's different. So in this case, for node A, right? So let's check with this rule. It has no parent, right? But it has one child, that is C, right? So now the C is given. And then we'll check if this child's parents is given. So the C's parents is A, right? So it's just the same, okay? So we're talking about the random variables, which is not A. So in this case, this rule is actually satisfied. So its child is given. So we know A and B are conditionally independent given C. And how about this one? will A and B conditionally independent given C? No or yes? Okay, let's just check with this rule. For A, what is the child of A? That is C, right? Now, C is given, right? Okay, and then what is the parent of A? There's no parent. Okay, so we can just say parent is given. And then what is the child's parents? That is, C's parents is also B, right? But B is not given. So we cannot say A and B are conditionally independent given C. Okay, we can just prove this conditional independency by using this formula. This is just the basic definition of conditional independence. Let's just review the above three examples. So in the first example, okay, we have, this is the conditional the PAB given C, right? So this, by using the definition of conditional probability, we can just write it in this way, right? So we have a joint probability PABC, right? And then we can just using this Bayesian network to rewrite this term into the three terms, right? So this is PC, this is PC, so they just cancel out. And this just satisfies the definition of conditional independence, right? So this is how to prove it by using the basic probability. And the second one is just as same. So we can just write this as this way, and we can see this PA over PC. This is just the PA conditional C, right? So we know they are conditionally independent. But the last one is not. You cannot prove this relationship. Okay, for the last case, there is actually an interesting phenomenon called explaining away. So here we have an example here. So those are the conditional probability tables. Okay, so this is the parameters we need to define this joint probability. And then now let's calculate two terms. The first one is P code given headache, right? How to do the calculation? So we can just, maybe I can just write here. So P code this is proportional to P code given headache. Oh, sorry. Right? And because in the network, we have three random variables. Therefore, to calculate this term, we need to cancel out, we need to marginalize the unwanted random variables, which is party. Right, so we can calculate this term, right, just by plugging in those numbers. And we can get two possible values for code. It's yes or no, or true or false, right? So we can just write these two, and we know they must sum together by multiply a scaling factor. And this makes us, this could help us calculate this scaling factor alpha, right? So we can get this probability, okay? And we can further calculate P code given headache and party. So in this case, we have one more evidence. That is, we know the party is being true, okay? And then we can calculate this conditional probability, which is 25. Okay, so we can see that, we can find that the first probability is larger than the second one. Okay, if we compare with the prior probability of code, so this one is smaller than this one. This is understandable, right? So if you are not feel headache, the likelihood of having code is low. But if you have this observation, you just increase your chance of getting code, right? So this one is larger than this one. This is understandable. But this one is interesting. You know you have headache, but you know you also go to party. And this will decrease the likelihood of being cold. Okay? This is because the cold could have two causes. The first one is headache, and another one is party, right? So sorry, a headache have two causes. The first one is cold. The second one is party. This is because you probably have some hangover, right? Okay, and knowing you have gone to party will somehow explain the code as a cause. So if you know you go to party, then you may know the headache is probably caused by party but not cold. So this will decrease its likelihood. So this phenomenon is called explaining away. And the reason we need to consider so just let's go back to the Markov blanket. We see that we need to consider the children's parents. Why we need to consider this? This is because of the explaining away, right? So this is the children's parents. So if we know the children's parents, this will affect the likelihood of code, the conditional probability of code, right? So it means P code conditional on headache is not equal to code conditional on headache and party. So we need to consider the children's parents. That's why we have it here in the rules of Markov blanket. Okay, so that's all for today's lecture. So in next lecture, we will introduce the inference method for Bayesian network. Okay, yeah, that's all. Sure. Yeah, I'll post it up after the lecture.你们喜欢用什么写？你们学过什么 ？C 加加。
所以第一个作业写的比较顺利。
那这样吧，我允许用 C 加加写，但是 C 加加你需要把 compile 全部 compile 好。你们是在那个 Linux 上面使用是吧？那可以，那就是要求是在 Linux 上，要不然到时候改作业很麻烦。
那就是可以用 C 加加，也可以用 Python。
对 ，C 加和 Python。
老师，那最后一个作业是要求过40%是吗？才能过
这个我得再 check 一下。这个相对比较简单，就是对，相对简单。